Say we have Gonzalo given us a talk. I guess many of you already know him, but just in case some of you don't know, he's a postdoc fellow at the Department of Physics in the University of Toronto. So he's obviously in the same building.
Yeah, just 2 floors down.
And he did his PhD in Heidelberg.
That's right.
And then he went to McGill before joining Toronto, and he's an expert on particle physics, particularly problems on related to dark matter. And so he will talk us about the role of dark matter in the emerging of.
Yeah, thanks, Rimpe, and thanks for the invitation to speak about this. I think, yeah, as Rimpe was saying, I'm in the physics department, but I very often think about cosmology and astrophysics in relation mostly to dark matter. So I guess this to say that if you ever have any question or anything that you want to discuss regarding dark matter in whatever astrophysical system that you're working on, I'll be happy to chat about that. So for today, I'll be talking about dark matter in particular in relation to supermassive black hole mergers. And here, kind of my main motivation, as we will see, is the fact that we can observe the gravitational wave emission from the supermassive black hole mergers. So maybe there's a hope that we can learn something about, how much dark matter there is in the surroundings of the supermassive black holes, and maybe also a bit about the particle physics properties of dark matter. So yeah, basically the way that I've structured this is that the first half of what I'm going to be talking about should be interesting to you, even if you don't care about dark matter. Yeah, hopefully everyone will take something away from this. And if I'm saying something that you think is too simple or something that you are not familiar with, please interrupt me at any point, and I'll be happy to focus on whatever you're most interested in. Yeah, because sometimes for me, because I come more from the particle physics side, there are things that are obvious to me from the particle physics, but maybe not so familiar for astrophysicists, and the other way around. Maybe I'm telling you something that's very standard to you, so let me know. Okay, so as I was saying, so the main motivation for me to think about this is the fact that we can observe gravitational waves from black hole mergers, and we know that we have observed them at different wavelengths or frequencies. So maybe just to get everyone in the same page regarding this, the kind of black hole mergers we're going to be talking about, we can look at the usual plot that you may be familiar with for gravitational waves, which is showing the characteristic strain that different sources have and different experiments are sensitive to as a function of the frequency. So here the characteristic strain is really just kind of the fractional change in whatever arm length you have in your interferometer, or as we will see, whatever distance that you're using, you're really measuring to look for these perturbations in space-time. So yeah, there are many. So all the plots I'm going to be showing here are log scale. So I'm not even going to bother writing log in the axis, but everything's log scale, just to be clear. But there are a couple of interesting frequencies. One is around like 100 hertz or so. So these are the frequencies at which astrophysical black hole binaries, so mergers of solar mass black holes, are going to be emitting in. And also, these are the frequencies that Earth-based interferometers like LIGO and Virgo are sensitive to. So, I mean, these kind of from the bottom, we see the source, and this is kind of the sensitivity of our experiments, say LIGO, Virgo, and all other interferometers. And I guess maybe I should put here some units. I think typically, like the typical strains are at the level of 10 to the minus 2 order of magnitude here. So this is at high frequencies, 100 hertz. I'm not going to be talking about those today. Then at slightly lower frequencies, say around millihertz or so, that's where future space interferometers will be sensitive to, basically things like LISA. And the things that they will be able to see are typically mergers of heavier black holes. So in this case, kind of the signal around here is made up of, say, 10 to the 4 mergers of 10 to the 4 solar mass black holes. but also extreme mass, what's called extreme mass ratio in spiral. And this corresponds to astrophysical solar mass black holes falling into a supermassive black hole of, say, 10 to the 6 or larger solar masses. And of course, this is just thematic. There's a range of frequencies and other things. I'm not going to be talking about this today. What I'm going to be talking is at way lower frequencies, all the way down to nanohertz frequencies. And that's where what we use to detect gravitational waves basically is pulsar timing. So pulsar timing arrays and are sensitive, like have a sensitivity curve that looks something like that. I think this is 10 to the 14-ish or so that they can be sensitive to. And the way that gravitational waves are detected here is just, we have a bunch of galactic pulsars, millisecond pulsars that we're very precisely timing. So the arrival time of their pulsars, we look at them and basically look for small deviations in how long these pulses from these pulsars are taking to arrive. And because, if there is some gravitational wave oscillating at some very low frequencies, then the distance that the light's traveling from these pulsars to us will be slowly fluctuating, and we can look for basically these slow fluctuations, these fluctuations in the arrival times for the lights in Fourier space. And this is how we can look for gravitational waves using pulsar timing arrays. So of course, this is this is again something that's not easy to do because the pulsars themselves are very precise clocks, but they have some small deviations. And then we're trying to look at many different pulsars and correlate the arrival time. So technically, this is very challenging, but this is something that these experiments are able to do. And what's interesting here is that here, somewhere here, the system that would emit gravitational waves at these frequencies are mergers of supermassive black holes. In particular, very massive black holes with mass up to 10 to the 9 solar masses or so. So these supermassive black holes would merge when the galaxies that host them merge. And therefore, by understanding what's the rate and what are the masses and what's the gravitational wave emission from the supermassive black holes, there's a lot that we can learn about galaxy evolution and the formation and the masses of supermassive black holes. So for those of you who may not be familiar with the way that usually gravitational wave strengths are measured, there are usually two different quantities that people quote when writing sensitivity curves and stuff. One is the characteristic strain in Fourier space. For instance, this is really just the spectrum of this can be related to the power spectrum of the fluctuations in these differential lengths due to the passage of a gravitational wave. And the other way that people usually parameterize is using the energy density in the gravitational waves. So we have the characteristic strain. HC, but also the gravitational wave spectral density, omega gravitational waves. And I'm going to use both throughout the talk. So that's why I wanted to introduce them. And the good thing is that it's quite easy to relate from one to another, the energy density in gravitational waves. So again, this is a bit more precisely the fractional energy density normalized by the critical density of the universe. So this is why, as you see here in this relation, we have this factor of the Hubble rate squared. Wait a second, because yeah, so this equals 2 pi over 3 hn f squared. There's a factor of the frequency squared, and then the characteristic strain squared. Yep.
So that
per unit log frequency. Yeah, yeah, yeah. I can define it now, I guess. It may be easier. So the definition of omega gravitational wave here is just 1 over the critical density times c squared. I'm trying to keep track of factors of c squared, but in particle physics, we usually set it to 1. So forgive me if like some of the formulas include c squareds and some others do not, because I'm using to just drop them. So this is the energy density in gravitational waves, normal per unit log frequency. Yeah, so this is the way how this is defined. Yeah, and so the reason why this is a relevant quantity is that what we're gonna be carrying most for these very low frequency gravitational waves are usually not the gravitational wave emission from a single supermassive black hole merger, but the integrated emission of all the supermassive black hole mergers across cosmic history. So this is usually called the stochastic gravitational wave signal, because we're not looking, as I was saying, specifically for one single merger, but just from the combination of all mergers, meaning that what you get here is just some isotropic background that's passing through your detector. Okay. So then what we care about, and I think there's a neat derivation, is not about a single gravitational wave emission, but the stochastic gravitational wave background. So as I was saying, the question now is, what can we expect from, look, what can we say in general terms for what the signal that these pulsar timing arrays may be expecting to see from all these supermassive black hole mergers? So there is a very nice theorem due to Finney in 2001 that basically characterizes what these stochastic gravitational wave backgrounds look like. Yeah, so this is, as I was saying, what we care about is this, an important quantity for this is the present, so this is the present day energy density of gravitational waves per log frequency interval. And here I say present day because the gravitational waves are gonna be emitted in a series of redshift. So we have to take into account that this frequency is changing from when it was emitted back at the redshift that the source is emitting to the redshift that we're detecting them now today. So a quantity that's useful to calculate now is the total energy density in gravitational waves that comes that would be coming from this, from such a signal. And for that, basically, the only thing that we have to do is to integrate this quantity over frequencies. And as you pointed out, because we're defining is per log frequency, we just have to integrate over this. Now, so the only thing that we need really to do this integral is to remember that the critical density of the universe is 3h0 squared over 8 pi g. And then we can use this relation between the characteristic strain and the energy density to rewrite this integral in terms of the characteristic strain. So in some sense, the way I see it is that the characteristic strain is really kind of the experimental quantity. This is what's relevant for actually measuring gravitational waves, because this is telling us how much strain is associated to the waves. But maybe this quantity, the energy density, is kind of more theoretically clear. So that's why I'm going a bit back and forth between the two. But basically, just writing down that relation, we can write this total energy density in terms of the characteristic strain of the stochastic background. Just like this. Okay. So this is a way that we can calculate the total energy density in gravitational waves from the point of view of what we're seeing today at, in our detectors or at present day. Now we can look, so we can look also at things from the point of view of the sources. So what we care about here for the sources is, these sources are, these supermassive black holes are going to be merging, emitting gravitational waves at a whole range of frequencies, depending on their orbital separation and how it is changing. So what we care about here is the total gravitational wave emission throughout the whole merger process, basically. So the quantity that we care to calculate is the spectral, the energy spectrum of gravitational waves emitted by the source. So you can think, for instance, I don't know if this picture is useful or not. You can think of putting the merger, the two merging supermassive black holes inside a box, and then measuring all the gravitational wave, all the energy that's being emitted into gravitational waves from this orbit across its whole lifetime. So anything that's crossing kind of through the border, through the borders of this box is going to be contributing to the total energy density in the stochastic background. So as I was saying before, something that becomes relevant here, and we have to be careful, is that F is the frequency of the gravitational waves at detection, but we have to distinguish this from the what I'm going to call FR, which is the frequency of the gravitational waves at emission. Because gravitational waves are radiation, we know that the frequency is just going to be redshifting as the scale factor. So it's 1/z because we're detecting at redshift 0, and the source is emitting at some redshift z. Okay. So I mean, what I'm looking to do now is to calculate this expression, the total energy density of gravitational waves, in terms of the different sources that are emitting. So with this, I know how much energy a single source is emitting. The other thing we need is the number of sources per unit redshift, which I'm gonna write the n over dz. Okay, so we know how many sources we have per unit redshift and how much energy in gravitational waves each source is emitting. So then we can very easily calculate the energy density in gravitational waves today. So this is the integral over redshift, and also the integral over frequency. And here I'm going to be integrate, at a given redshift, the source is going to be emitted at the frequency fr, but we're detecting it. So we want to calculate the energy density at today. So we have to redshift this frequency. And then this is the spectrum of the source that we're calculating. I guess I should have written FR there. So this is what the source is emitting. So it's the frequency of the source that comes into play there, times the redshift distribution of sources. Okay, so this is, so basically this is another way that we can express this quantity. Now, so of course, we could now equate these two. What I want to do is equate the integrand. So for that, I need to swap the integration order. So let's say I first integrate over frequency. I want to also do the log integral here, and I want to swap FR. So once I swap the integration orders, I can just write F. Well, I can just write F using this relation, and so the log, the d log F. So I can just change the FR for R here at this stage, and then I integrate over redshift, and I have dn dz, this factor of 1 plus z, and then I've divided by f, so or fr, so I should also multiply by fr. So here I have fr dE gravitational waves. And of course here r, so you know, when we do this integral, r should be converted to fr should be converted to f depending on the redshift that this contribution comes from. So now, because I know, so we have two different expressions for the energy density, the total energy density in gravitational waves. So we can equate both. And since this is an equality, we can just equate the integrands, and this gives us kind of the main result for what the gravitational, so the characteristic strain spectrum today is from a collection of sources with a given redshift distribution. Then equating both things, you get that rho c squared omega gravitational waves as a function of the frequency at the source, or also written in terms of the characteristic strain, looks like this. Yeah, so this is kind of going to be, this is one of the key equations for these stochastic backgrounds. So as you can see so far, I have really not specified much. So this is a result that's pretty generic. So any kind of source, as long as we know what its frequency at emission of gravitational waves and its redshift dependence, so we can use this expression for. So in particular, this can be used for supermassive black hole mergers, as we're going to do, but also for some other cosmological sources, say cosmic strings or things like that that may be emitting gravitational waves. So this is a general expression. Okay, but let's now focus on black hole mergers. Basically, so we just assume that the black holes are orbiting in a circular orbit. And this means that, so the only thing that we're gonna need kind of to calculate the, so what now we're trying to do is to calculate this term for supermassive, for black hole mergers. The only thing that we need to know is the gravitational wave emission for a circular orbit has frequency that's twice the orbital energy. So this is twice the orbital energy. So this is just 2 times square root of g m1 plus m2, so the masses of the two merging supermassive black holes, over pi squared r cubed. And r is just the orbital. It's just the separation between the two black holes in the orbit. So of course, as the orbit shrinks, this is something that's going to be changing. And this is basically a relation between what's the frequency of the gravitational wave that's emitted at a given black hole separation. And now things are very easy because so we know so under the assumption that these black holes are the orbit of this binary is shrinking due to just gravitational wave emission, we can very quickly calculate how much energy. So the energy that the orbit, like the energy that's being emitting the gravitational waves, is equal to just the orbital energy of the system. So this is G m1 m2 over 2r. Maybe with a minus sign there. I'm going to be a bit cavalier with minus signs here and there. You can trust that, you know, if one properly takes into account whether the energy is being emitted or losing, these things add up correctly. But we just know, we know the expression for the orbital energy, and then the gravitational wave emission as a function of frequency is just minus the orbital energy that the system is losing as a function of frequency or radius, because both are related by this expression. So we can multiply and divide by dr, and then this piece we can calculate from here. This piece we can calculate from here. So I'll skip the algebra and just write the result for what comes out. This is pi over 3, 1 over g times this curly m. That's called the chirp mass. It's usually used in gravitational wave in supermassive black hole, in black hole mergers and gravitational wave emissions, and then pi over the frequency to the 1/3. And this chirp mass is just some reduced mass. I'm gonna write it here. I think this is m1, m2 over m1 plus m2 to the 1/3. Okay, and now, so the important thing that we know that we get here is what the frequency, what the spectrum, the frequency dependence of this quantity looks like. Because now we can go up here at this expression and we conclude that the characteristic strain as a function of f is going to be proportional to, well, there's and 1 over f squared here, 1 over f there, and this has 1 over f to f to the 1/3. So h squared is proportional to, after we add everything up f to the minus 4/3. Or of course, this means that the characteristic strain is expecting to have a frequency dependence of f to the minus 2/3. So this is a pretty general result, a pretty easy way to calculate that the signal, like the frequency dependence of the signal that we should be expecting to see from this cumulative emission of supermassive black hole mergers should have this frequency dependence. And this is very generic. We haven't needed to say much about this this redshift dependence of the number of sources or anything. Of course, calculating the amplitude for the signal is very tricky because it involves this term here, and this term depends on what is our assumption for the well, the mass distribution for the supermassive black holes, the redshift distribution for the supermassive black hole mergers, which can be connected to the galaxy merger rate. So these are things that are much harder to calculate. But this frequency dependence is fairly robust against those. Exactly. Of course, this once the black holes are merged, there is a high frequency cutoff for the signal, and there should be also be some low frequency cutoff for it. You know, when the black holes are very far apart, and gravitational wave emission is not going to be very relevant. We're going to be talking about that in a bit. But yes, I agree. There's a cutoff, a high frequency cutoff for this. Okay, so with this we have like a pretty robust expectation for what, except for the amplitude of the signal, which is something that I'm not going to get into today, but of course, it's a very interesting thing to calculate and estimate. So we have a reasonable expectation for what pulsar timing arrays should be seeing in this frequency spectrum at around nanohertz frequencies. So let's say this is around nanohertz frequencies. I'm going to be just showing this. So we expect that under this assumption, there should be this should be just a power law with slope minus 2/3. And indeed, this seems to be very close to what pulsar timing arrays saw. So nanograph and all the other pulsar timing array collaborations saw some evidence for the presence of stochastic gravitational wave backgrounds in their data. And what they see, of course, with huge error bars, is something that kind of looks like it, but maybe not exactly so. And so it seems to be kind of a bit softer, of course, with huge error bars than what we would expect from this. And this was kind of one of the reasons why people started speculating, oh, maybe the signal that we're seeing here is not due to supermassive black hole mergers, but due to some other processes like phase transitions in the early universe, cosmic string, or the gravitational wave emission from topological defects. But I guess what I'm going to be arguing is that there are things that there are some assumptions that we have made here that will change this slope in a way as to make it better compatible with this. So I think in this derivation, we have made two key assumptions. The first one is that mergers are fast compared to the Hubble rate. So we've essentially assumed that each merger occurs instantaneously at one fixed value of the redshift. That's fairly reasonable, even if so mergers last for a few hundreds or mega years, even a few giga years. This doesn't lead to any significant correction to this source. It's only when the mergers get very long, like compared to 8, that things change a lot. And the other assumption is that basically all the orbital energy goes into gravitational wave emission. And I'm gonna, what I'm gonna be discussing next is that these two assumptions, and in particular, the second one, is probably not a good assumption to be making, and it leads to a change in the spectrum that makes the agreement between data and theoretical expectation better. Okay, so any question up to this point? Anything that's not clear or anything that's too simple? Okay, so if not, I'm gonna get a bit into what dark matter comes in. So far, I've just been talking about standard astrophysics. So the dark matter that I promised you, I think I can also raise this. So as I was saying, there are those two key assumptions are strong assumptions, in particular because so I was saying that the first one that does probably not have much impact in the gravitational wave spectrum, but that was kind of simplifying things a bit, because there's something that you may have heard about that's called the final parsec problem, and which basically says that this first assumption is not only not a good assumption, but that most mergers may be taking longer than the age of the universe to merge. And of course, if that's the case, that really changes things, because if black holes do not merge, then this redshift distribution of mergers is 0, even if none of them was merging, or significantly suppressed and maybe skewed toward lower redshifts if mergers really take a long time to complete.
So this relates to how do you believe supermassive black holes do exist?
Not really. So that's a good.
If they can't merge with another big one, then they have grow by just
yeah.
Which is the content of today's book.
Yep. So this is a bit disconnected to that. I agree that there's the question of how they grow, but I think even if they're merging efficiently, mergers do not significantly are of dominant contribution to black hole growth compared to accretion. So so this is a bit separate from that. And here we don't really, I mean, we're not really sensitive to how they were born at the first place because from the practical point of view that I just care about explaining the signal, right? If this signal is really coming from supermassive black hole mergers, then this is evidence that black holes do merge. So I just need to find a way to make them merge faster. And then this signal is coming from the mergers of like 10 to the 9, mostly 10 to the 9 and heavier supermassive black holes at fairly low redshift. So after they've accreted a lot of gas, they've merged maybe a few times already. So they've lost a lot of the information about the first stages of growth. And we know, kind of from the practical point of view, we know that these large black holes exist today in the low redshift universe. So we also expect them to have merged or to be merging at some rate. So, I mean, that's a good question and a good point. And some people have, and this relates a bit more to what I was saying. I'm not going to be discussing the amplitude of the signal, because that is very sensitive to really how many of these very large supermassive black holes there are around, how fast they merge. And some people argue that, you know, the amplitude that you need to explain the signal is at odds with standard expectations. But this is something that's a bit, that's another topic of discussion.
Well, if you had two supermassive black holes and they got stuck, couldn't merge, what would it look like to us? Could we tell that there was actually bigger?
Yes, so you could look for what people call dual AGNs for these very large masses. And I think so that's something that people have been looking for, like just through the electromagnetic emission of these dual AGNs, which should be slightly different to that of single AGNs. And I think so far people have really only found one candidate of a pair of supermassive black holes that are orbiting like at parsecs of a few tens of parsec distances. So this is kind of some maybe indirect evidence that they seem to, in most cases, merge efficiently. But of course, this is, you know, there may be a lot of huge observational bias. I don't know exactly how many of them we're really able to see through electromagnetic observations compared to how many we'd really expect. And I think the point is that so the amplitude so the number of mergers that you need to explain the PDA signal is not much. So the whole signal, even if I'm talking about this stochastic signal, the fact that it's a cumulative emission from many mergers, it may be the case actually that this is just order 10 of 1,000 mergers that are giving you the whole signal. So you do not need so many at all, as long as they are huge and massive enough to be emitting in this frequency range. So then, of course, you know, it becomes very tricky, because if it's only a few, then you know you have to trust like all your observational systematics and bias very well to be able to say, oh, there could not be 10 or 12 supermassive black holes having merged in the last couple of giga years. So yeah, it's a very interesting question. It relates a bit more to the amplitude of the signal that I'm not getting much into today because of all these complications. Precisely, I'm looking a bit more just at the frequency dependence, where the things that we can say are a bit more robust. So in the interest of time, I'm not going to be discussing much about the final parsec problem. So this is a lot about the dynamics of two merging supermassive black holes in a galaxy, where you account for the interaction of the black holes with the gas and the stars around. So this is basically a dynamics problem that I'm sure you know way more about than me. So I will just say that basically there are two regimes when the black holes are larger than, say, tens, order 10 parsecs or so, then dynamical friction with stars in the surrounding environment. So basically, the two galaxies merge, and then the black holes migrate towards the central position of the merged galaxy through dynamical friction. Basically, just dynamical scatterings with the field and stars around them. So this is expected to be very efficient in bringing the black holes together down to, say, a separation of tens or a few parsecs or so. But at that point, the black holes are so close to each other that the orbital energy, so in order to efficiently extract a significant amount of orbital energy, the stars have to come very close to one of the supermassive black holes. And then, this is occurring at the very central position of the galaxies, the inner parsec or 10 parsecs or so. So there are not so many stars that have such a low angular momentum that they can come so close to the black holes. And the few that are get very quickly ejected through the interactions with the hard binary of the black holes. So this is basically like people have, of course, done a lot of calculation simulations to estimate this, and it still seems that when you get to a distance of around a parsec, these encounters with stars do not seem efficient at making the supermassive black holes merge in timescales less than many or a few or even many giga years, or even in timescales shorter than the lifetime of the universe. Then when the separation is smaller than about a fraction of a parsec or so, that's when gravitational wave emission really kicks in and can drive the in-spiral by itself. And at these separations, there's also maybe gas drag that may become important. But the point is that there are some intermediate separations here at orbital separations of around a parsec, where interactions with stars do not seem to be effective enough, and still gravitational waves is not effective enough, and the binary may stall at these separations. But of course, if we really think that the signal is coming from supermassive black holes, this means that there must be something here. Now, maybe we're not properly accounting for all the gaseous effects, for all like how fast the stellar environment is being replenished around supermassive black holes for them to keep extracting energy from the supermassive black holes in order to reach this parsec of separation. And I guess what I'm going to be arguing is that something else that could be doing something important here is dynamical friction with the dark matter, basically. And maybe, so this is, of course, so this is something desirable. We want to solve this final parsec problem. We want to make the mergers, the supermassive black holes actually merge within the lifetime of the universe. But this also has an important implication regarding assumption 2. And now is that not all the orbital energy is going into gravitational waves. There's this other extra source of energy loss that becomes relevant here. And this changes a bit the derivation that we have done there, because now, in a fairly trivial way, if we want to recalculate the gravitational wave spectrum, taking into account that maybe not all the energy is going into orbital energy, then we can write this. We can write this as the power going into gravitational waves, again, assuming a circular binary and everything. So IS divide by dt, both in the numerator and denominator. And now I can relate the frequency to the orbital separation through this relation over here, and rewrite this time derivative as the time derivative of the how the orbital radius is changing with time. And now I can I know how to relate this to the rate at which the orbital energy is being emitted, right? So the power loss in the orbit, which is just E dot orb, is just Gm1 m2 over 2r times r dot over r. So then plugging this in, I can basically rewrite this equation. Well, let me simplify. Let's call this prefactor, well, whatever, star. So what I get here, oops, is this prefactor star telling us how much is going, but now I get a ratio of the power going into gravitational waves versus the power that the orbit's losing. And again, like maybe some minus signs or whatever to account here to make things right. But this is basically telling us that the way that modified is that at every given frequency, we have to know how much power is going into gravitational waves compared to how much power is going into the orbital evolution at that radius, right? So, I mean, for me as a particle physicist, I think of this as some sort of branching ratio calculation that tells us how much energy is going into different channels. And what this will mean is that here for the spectrum, so this is, so just with this relation, so as frequency increases, the radius decreases, right? So higher frequencies correspond to a smaller radii. So at high frequencies, we do not expect that things are going to change much because at small separations, gravitational wave emission is just very effective. So we expect that here, this slope will not be modified much through interactions with the environment, but at large frequencies, which corresponds to separations larger than a fraction of a parsec or so, we expect that there is something that's making the black hole merge faster. And this means that most of the orbital energy, instead of going into gravitational waves, is going to be going into this something else. And this will lead to a softening of this spectrum at low frequencies. And this is exactly what makes what is kind of needed to make the agreement with the data better. So I guess this is just to say on very general grounds that this was kind of to be expected because there's this final parsec problem that has to be solved somehow. And this correlates with the softening of the spectrum necessarily because of these arguments at small frequencies. And I guess the point that now I'm going to be quickly trying to make, and I guess I'm going to just say it in words because we're almost over time, is that dark matter dynamical friction is something that could be relevant in this intermediate separation at something that could lead to softening the gravitational wave spectrum, and the extent and the position of this softening is something that we can relate to like particle properties of the dark matter, and in particular to the dark matter self-interactions. And I guess I do not have, unfortunately, time to get into detail into what we actually did for the paper, but I guess maybe just the main argument for why we need so why we think we may be sensitive to particle physics properties of the dark matter is that all this dynamical friction that's making the black holes lose orbital energy is going into heating up the dark matter particles in the environment of the black holes. And basically, in the same way that the stars get ejected from this interaction with when they interact with the black holes, the dark matter is going to be ejected from the environment of the black holes. And this means that one can do a quick back on the envelope calculation. This means that all dark matter cannot possibly have a significant impact on the merger because of back reaction. Basically, the same thing as with start happens. Collision-small dark matter particles get ejected from the central parsec of the region, and therefore they cannot generate a significant amount of friction. But now, if dark matter has self-interactions, So if we talk about self-interacting dark matter, now, of course, the dark matter particles will still be getting dispersed, interacting with the black holes, but now there is a relaxation timescale that's associated with the self-interactions of the dark matter that's going to be much faster than the one that the gravitational one that would be replenishing things for stars or cold dark matter. And that's what really can make the difference, because if the self-interactions are strong enough, so the self-interaction rate is large enough, the relaxation timescale is going to be small enough, short enough, such that, you know, as the dark matter particles are being expelled from the final part, from the innermost parsec of the galaxy, they're going to be replenished from through this self-interaction driven thermalization. I know this was very fast, so if you're interested, I'm happy to discuss more about this. But I'll get just to the punchline. Basically, after we account for all these self-interaction effects and the impact on the dark matter profile in this inner part of the galaxy, what we find is that we need a very particular kind of dark matter model in order to solve the final parsec problem and get a good fit to the data. So we need like self-interaction cross-section that has a velocity dependence, as happens for a massive mediator. And for those of you familiar with the self-interacting dark matter literature, the self-interaction cross-section per unit mass that we need is at the level of centimeters squared per gram. And this is exactly the kind of self-interactions that people like to explain some small scale problems of cold dark matter. So I guess this is what kind of got me interested. You know, we started playing around with what would dark matter need to do in order to have a significant impact here. And after kind of a series of non-trivial requirements, you find that this very specific model is the only thing that can have a significant impact. And it happens to be the same model that people had previously considered and liked for some completely unrelated reasons. So I guess that's why I find this result to be interesting, because it seems to be pointing towards a direction that's motivated by other considerations. Because I mean, at the end of the day, you know, all these things are very messy. There's a lot of uncertainty because we don't exactly know what there is really in this innermost parsec of the galaxy after a merger. So of course, all the things that we're doing here so far are just, you know, order of magnitude estimates back on the envelope calculations with huge uncertainties, right? So if you get that you need some particular model, you may say, fine. But if the result is that, well, the things that you need are things that are reasonable and maybe even preferred because of some other considerations, then I think this is a motivation to think a bit more seriously about this. And yeah, I think with this. Okay.
Oh, yeah. One is that the moment in the Milky Way, with lots of other galaxies, the baryonic matter is by far dominant in this inner region.
Yep.
So the point here is that despite that fact, the fact that you can replenish
exactly
the dark matter using the self-interactions, that sounds like it's putting the dark matter into a similar category as the gas drag.
Exactly. It's something like that. The difference here is that, you know, stars only relax gravitationally. That's very slow. So if you have another mechanism to make things relax, as you were saying, as happens with collisional gas, then that's what helped you. And even if, you know, the density may be subdominant to other components, it can have a significant impact over kind of the whole time scale that you need to make the black holes merge. Yeah.
Second sort of question, numerology question, is centimeters squared per gram. Get out of cross-section per proton mass. Is that just a complete coincidence because that's electromagnetism, or is some underlying reason that would have the same value?
I would know. That's a good kind of model building question for kind of the particle physics side. I agree that you know, it's a reasonable thing. It's not a like completely unreasonably large self-interaction cross-section or completely ridiculous one. So you can more or less easily think of models that can reproduce, that can give you this self-interaction cross-section. And I, for instance, can quickly think there are models where like the dark matter may be similar in some sense to the visible matter, and dark matter may be made of neutrons, something like neutrons or dark neutrons, and then those would be scattering at some rates similar to this. Yeah, so yeah, I can say that it's a bit speculative at that stage, but yeah. I guess the interesting thing is that now you can hope to use both. This data is going to get better, right? So as it gets better, you may start to get a better handle on the different thing, on actually what on the dynamics, right? And the hope is, can you at some point distinguish between the softening that you expect from dark matter and the softening that you may expect from some other baryonic processes? So that would be the kind of the interesting stage for this.
The dark matter friction, like from Chandra-Price dynamical friction with the dark matter.
Exactly.
I was under the impression that the spike would have probably vanished, but if you have a supermassive black hole.
Yeah.
Wait, that's what you mean by the CEM back reaction.
Exactly. This is what I mean. Like you're completely correct. So what happens here is that the dark matter profile looks something like NFW on the outside, and then here in the kind of few inner parsecs, the gravitational potential of the supermassive black hole is dominant over the self-gravity of the dark matter, and then you may expect that there is an increase in the dark matter profile. Of course, if now you have black holes moving around and steering all this, then you may expect that this gets flattened, which is a very reasonable expectation. I agree. But then if you have this if you have these self-interaction relaxations, you have to take into account this relaxation and the effect of the self-interactions. And what you find is that probably you get something that's not as steep as you were expecting to begin with, but also not completely flat. Which and this is one of the ways how you can constrain the self-interaction cross-section by the fact that you do need some amount, like some significant dark matter density to be there in order for dynamical friction to be efficient. Yeah, I went very fast through this because there was no time. Mm-hmm.
Firstly, would actions be CDM? Would actions be decision CDM?
For practical purposes, yes, I would consider for these actions to be CDM. Yeah, so actions do not have significant self-interactions that they would lead to fast enough thermalization. People have speculated about ultralight dark matter, so ultralight axions, but again, I haven't seen convincing evidence that you can get this sufficiently fast relaxation timescale. Although nominally it looks like they can be very good at generating friction, I don't know about the back reaction, and I don't know if that's something that people have looked carefully enough at.
Have axions been discovered in the context of supermassive black hole mergers?
Yep.
They have been postulated to exist when you have these supermassive black hole mergers, and they may constitute part of the background, gravitational wave background.
Yes, that's an assumption that I'm making here, of course.
Okay.
It's a possibility that the signal is coming from something else, but I think kind of this is the most straightforward astrophysical explanation, and it seems to fit well with what we're saying. Bearing the issue with the amplitude, that's a very complicated question. So I'm willing to accept that maybe models were not quite on point for the amplitude there, and they may get revisited. Same thing to what happened with LIGO. At first, we were very surprised about the amount of mergers.
Thank you very much. May I request your email address so that I keep in touch with you?
Sure. Yeah, I don't know. Like I don't know what would be. So I can type it in the chat, or maybe Rinpei can put me in touch with you. Yeah.
Yeah, maybe. Do you want me to give my email address?
I can send his email to you.
Yeah, thanks.
Thank you very much. I do hope to be in touch with you.
And thanks, everyone.
And
It's interesting because the interactions have to sort of change angular momentum.
Philip, is this your phone?
Oh yeah, it is. Interactions have to change angular momentum, but they're not dissipative interactions, right? So for some reason.
Oh, that's a very good question. Like the assumption here is that it's elastic interactions, but I think it's worth thinking about dissipative interactions, because that will naturally help, you know, to clamp things closer together and get more density. Yeah.
But then you're sort of reproducing the it's back to the mirror dark matter. You've got an entire
exactly
mirror world there.
Yes, but it's a good question. I mean, you can be a bit more like, it doesn't need to be like a complete distance.